Phasor representation of resistance R. A resistor behaves the same at any frequency, it simply opposes the flow of current like friction opposes motion. In the phasor complex number world, its impedance is a real number with no imaginary part. Z sub R equals R. On the complex plane, this point sits on the horizontal real axis. For a concrete example, let R equal 50 ohms. The phasor impedance is the point 50, 0 and can be written as Z sub R equals 50 plus J0 ohms. Because the angle argument of a pure real number is 0 degrees, the current and voltage phasors are perfectly in phase, they rise and fall together. This is why a resistor consumes only real active power. An inductor stores energy in a magnetic field, similar to how a flywheel stores kinetic energy. Its opposition to current changes grows with frequency, and the voltage leads the current by 90 degrees. In phasor form, the impedance is purely imaginary and positive. Z sub L equals J omega L. Here J is the imaginary unit, omega is the angular frequency, radians per second, and L is inductance, henries. The point lies on the vertical imaginary axis above the real axis. Example, L equals 10 millihenries, which is 0.01 henries, omega equals 2000 radians per second. Z sub L equals J times 2000 times 0.01 equals J 20 ohms. So the phasor is 0,20. The angle of this impedance is positive 90 degrees, meaning the voltage phasor leads the current phasor by a quarter cycle, just like the force needed to spin a flywheel must be applied before the wheel actually accelerates. Phasor representation of capacitance C. A capacitor stores energy in an electric field, analogous to a spring that stores mechanical energy. It resists changes in voltage, causing the current to lead the voltage by 90 degrees. Its impedance is purely imaginary but negative. Z sub C equals 1 over J omega C equals negative J over omega C. The phasor point sits on the vertical axis below the real axis. Example, C equals 5 microfarads equals 5 times 10 to the minus 6 farads. Omega equals 2000 radians per second. Z sub C equals negative J divided by 2000 times 5 times 10 to the minus 6 equals negative J 100 ohms. Thus the phasor is 0, minus 100. Its angle is minus 90 degrees, indicating the voltage lags the current by a quarter cycle, just as a spring pushes back after being stretched. Series combination of R, L, C. When R, L, and C are placed end to end, their impedances simply add because the same current flows through each element. Z series equals R plus J open omega L minus 1 over omega C close. The real part R stays on the horizontal axis, while the net reactive part inductive minus capacitive sits on the vertical axis. If the inductive reactance omega L is larger, the overall impedance points upward inductive. If the capacitive reactance is larger, it points downward capacitive. Numerical example, R equals 50 ohms, L equals 10 millihenry, C equals 5 microfarad, omega equals 2000 radians per second. Inductive reactance X sub L equals omega L equals 2000 times 0.010 equals 20 ohms. Capacitive reactance X sub C equals 1 over omega C equals 1 over 2000 times 5 times 10 to the minus 6 equals 100 ohms. Z series equals 50 plus J open 20 minus 100 close equals 50 minus J 80 ohms. So the total impedance is a vector 50 ohms to the right and 80 ohms down. Its magnitude is absolute. Z equals square root of 50 squared plus 80 squared approximately 94.3 ohms. And its angle phase is phi equals arctan of negative 80 divided by 50, approximately negative 58 degrees. The negative angle means the overall circuit behaves more like a capacitor current, leads voltage. When the three elements share the same two nodes, the easier quantity to add is admittance, the reciprocal of impedance. The total admittance is Y parallel equals 1 over R plus 1 over J omega L plus J omega C. 1 over R is a real conductance term. 1 over J omega L equals negative J over omega L is a negative imaginary capacitive term, because an inductor in parallel looks like a capacitor from the admittance viewpoint. J omega C is a positive imaginary inductive term. The total impedance is the reciprocal of the total admittance. Z parallel equals 1 over Y parallel. Numerical example, use the same component values as before. Conductance G equals 1 over R equals 1 over 50 equals 0.02 Siemens. Inductive admittance Y sub L equals 1 over J omega L equals negative J1 over 2000 times 0.010 equals negative J0.05 Siemens. Capacitive admittance Y sub C equals J omega C equals J 2000 times 5 times 10 to the minus 6 equals J0.01 Siemens. Y total equals 0.02 plus negative J0.05 plus J0.01 equals 0.02 minus J0.04 Siemens. Now take the reciprocal Z parallel equals 1 over 0.02 minus J0.04 equals 0.02 plus J0.04 over 0.02 squared plus 0.04 squared equals 0.02 plus J0.04 over 0.002, approximately 10 plus J20 ohms. Thus the parallel network looks like a resistor of 10 ohms in series with an inductor of about 20 ohms reactance. Its magnitude is square root of 10 squared plus 20 squared equals 22.4 ohms, and the angle is plus 63.4 degrees indicating net inductive behavior. Explanation: phasor voltage current relationships for RLC. In phasor form, Ohm's law becomes V equals IZ. The angle of Z tells us how voltage and current are shifted relative to each other. Resistor Z sub R equals R angle 0 degrees. V and I point in the same direction, they rise and fall together. Inductor Z sub L equals J omega L angle plus 90 degrees. Voltage leads current by a quarter cycle. Visualize a water wheel. The torque voltage peaks before the wheel speed current does. Capacitor Z sub C equals negative J over omega C angle minus 90 degrees. Voltage lags current by a quarter cycle like a spring that compresses current before the force voltage appears. Sample phasors at omega equals 2000 radians per second. Assume a sinusoidal current phasor I equals 1 angle 0 degrees amperes. Resistor V sub R equals 1 angle 0 degrees times 50 equals 50 angle 0 degrees volts. Inductor V sub L equals 1 angle 0 degrees times J20 equals 20 angle 90 degrees volts. Capacitor V sub C equals 1 angle 0 degrees times negative J100 equals 100 angle minus 90 degrees volts. If you draw these three vectors on a complex plane, you will see the resistor voltage on the horizontal line, the inductor voltage straight up, and the capacitor voltage straight down. Adding them tip to tip gives the total voltage for a series RLC. Power calculations using phasors. Real active power, reactive power, and apparent power are derived from the voltage and current phasors. Apparent power, S equals V RMS I RMS. Units VA, it is the magnitude of the complex power vector. Real power, P equals V RMS I RMS cosine phi, where phi is the phase angle between V and I. Reactive power, Q equals V RMS I RMS sine phi, units var. Example series RLC. Use the earlier series impedance Z series equals 50 minus J80 ohms. Magnitude of impedance, magnitude of Z approximately 94.3 ohms. Phase angle, phi equals arctangent of negative 80 divided by 50, approximately negative 58 degrees. Current leads voltage. Assume the source supplies a sinusoidal voltage with peak amplitude Vm equals 100 volts. RMS voltage is V RMS equals Vm divided by square root of 2 equals 70.71 volts. Circuit current RMS. I RMS equals V RMS divided by magnitude of Z equals 70.71 divided by 94.3 equals 0.75 amperes. Apparent power, S equals V RMS I RMS equals 70.71 times 0.75 approximately 53.0 volt amperes. Real power, P equals S cosine phi equals 53.0 cosine negative 58 degrees, approximately 28.2 watts. Reactive power, Q equals S sine phi equals 53.0 sine negative 58 degrees, approximately negative 44.9 volt amperes reactive. The negative Q indicates net capacitive reactive power. The circuit supplies reactive power back to the source. The power factor is cosine phi approximately 0.53, lagging if the angle were positive, leading here because of the negative sign. Typical exam questions on phasor analysis. Below are 3 representative problems that students often meet in an introductory AC circuits exam together with brief solution outlines. Number 1, find the total impedance of a series RLC circuit. Given R equals 30 ohms, L equals 25 millihenries, C equals 10 microfarads, frequency F equals 60 Hz, omega equals 2 pi F. Compute X sub L equals omega L and X sub C equals 1 over omega C. Form Z equals R plus J times open parenthesis X sub L minus X sub C close parenthesis. Provide magnitude Z equals square root of R squared plus open parenthesis X sub L minus X sub C close parenthesis squared. And angle phi equals arctangent of X sub L minus X sub C divided by R. Number 2, determine the circuit current and power factor for a parallel RLC supplied by 120 volts RMS at 50 Hz. Compute admittances Y sub R equals 1 over R, Y sub L equals 1 over J omega L, Y sub C equals J omega C. Sum to get total admittance Y total. Take reciprocal to find Z total if needed. Current magnitude I equals V RMS times magnitude of Y total. Phase angle of current relative to voltage equals argument of Y total. Power factor equals cosine phi. Number 3, find an unknown capacitance that will make a series RL circuit resonant at 1 kHz. Resonance condition for series omega L equals 1 over omega C, therefore C equals 1 over omega squared L. Insert omega equals 2 pi times 1000 radians per second, and the given L to compute C. Verify that at resonance, the impedance reduces to just R and compute the resulting current, I equals V RMS divided by R. These problems test the ability to move between time domain sinusoidal sources and their phasor representations to perform algebra with complex numbers, and to interpret the physical meaning reactive versus real power resonance power factor. Practicing them builds intuition such as inductive reactance climbs with frequency, capacitive reactance falls with frequency, and the geometric view of adding vectors on the complex plane.